Greetings. This is Nate's rendition of homework assignment 11, problem 1, where we were given that x of t is a wide sense stationary stochastic process. We're also given that the autocorrelation of Rxx tau and the power special density Sxx omega. And we are charged to prove that the autocorrelation of XX to tau is real and even, and the spectral density of XX, of omega, is even and non-negative. Section A. Rxx of tau, by definition, is the product of 2 points. So the expected value is of t plus tau, and the other point is x of t. Basically, they prove to be commutable, so they're rearranged here, but the expected value as it nets out of the product implies that it is not only, it's real by definition, since the subsequent process emanates from random variables which appear on the real scale. Furthermore, the autocorrelation of XX, t comma t plus tau, is also equal to the same correlation, if you will, of a minus tau, and therefore they are even. So we have completed that part of this problem, and we will proceed to the next section directly. Greetings. This is a continuation of homework assignment 11, problem 1, part 2, where we're dealing with section B, and the challenge is to take the spectral density and to prove that it is even and non-negative. So we start here in section B with the spectral density XX of omega equal to the integral from minus infinity to infinity of the correlation of Rxx of tau times e to the minus j omega x d tau. Breaks down further into the integral over the same range of the correlation, but this time times the cosine of omega tau d tau minus j, the conjugate, over the same range, and I apologize for omitting for the interval for the integral of the correlation of xx. Oh, by the way, it's the same from minus infinity to infinity of tau, the sine of omega tau d tau. Here, there, we summarize, and we end up with 2 times the integral from 0 to infinity of the correlation of xx of tau, the cosine of omega tau d tau. And again, a further summarization, 2 times the integral over the range from 0 to infinity, the correlation of xx of tau, the cosine of a minus omega tau d tau. And that basically reflects the fact that as an even function, you get the same result So we approve one part of that challenge for section B, and the fact that it is not negative. As the spectral density of XX omega is, and that's the not sign, not negative. Okay. To the next portion, we are going to discuss, well, not discuss the example, which says in the book, but or in your notes. We have x of t equal to a bypass filter, an impulse function, if you will, that yields y of t. The impulse function h of omega is basically set that when equal to 1 over the interval of omega from omega 1 to omega 2, that it is less than omega 2 but greater than omega 1. Okay, and any other values is equal to 0 for everything else. Here, the expected value of the absolute value of y of t squared is greater than 0. And we can see the equation is equal to 1 over 2 pi, the integral from minus infinity to infinity of the absolute value of the impulse of omega squared times the spectral density of omega d omega, which is further equal to, which is further equal to 1 over 2 pi, the integral from omega 1 through omega 2 of the spectral density of omega. When this implies that W1 over the area is negative. So therefore, the spectral density of XX omega is greater than 0 everywhere. Thank you very much.